So, good afternoon. Welcome to the tutorial on A/B testing at scale. I'm Ronnie Kohavi. I'm going to do the kickoff introduction, but there's a lot of speakers, so why don't we first introduce them? And I'll put up the schedule so you can see approximately how we're going to handle this. I'm going to start off with the longest section. It's also the easiest technically, which is the introduction. And then Lucas, why don't you come in? He's going to do the design stats foundations, followed by Paul. Right? And then we got protecting users.
Me, Paul.
Pavel, designing metrics.
Nice.
Summit. And then developments by Alex over there. Okay, it's a rough schedule. We put a nice buffer at the end, which we may eat if you have questions in the middle, which is good. I encourage you to ask questions in the middle. So there is room to answer those. And if not, we'll leave some room at the end. Of course, we'll be able to stay at the end to answer any other questions that you might have. Okay, thanks folks. With that, let's get started. Okay, so I'm going to start with probably one of the most amazing examples that has happened to us. It's a true story. It happened in Bing. And I'm going to start just with sharing the idea first, which was a few years ago. And what somebody proposed was just to change the way ad titles were displayed. Actually, use a pointer, which is going to be easier. Okay, so here's the simple idea. You take the last line of the ad and you promote it to the first line, so the first line looks larger. Right? So here's one example, here's another example. You just promote it to the upper line. And if you look at the idea, you know, it's one of hundreds of ideas that were proposed. So, you know, we get a lot of those ideas. It's hard to estimate them. When you look at this idea, you're like, maybe. You know, who's going to make sure that this is really going to be a great idea or not? And of course, you know, because nobody thought this would be great, it got delayed. And, you know, we looked after this idea proved itself valuable, which I'll get to at the end, but we delayed in February and March and in April and in May and in June. And there's a lot of features that were stack ranked above this. But person made an observation. Wow, at this rate, it's not going to make it by the end of the year. We got so many things above it, but this is easy. Right? It's a simple idea that's easy to implement. So he went and implemented this in a few days and started a controlled experiment or an A/B test. These are synonyms. Or an A/B test is a specific example of a controlled experiment. For most of this talk, you can assume they're synonymous. And an interesting thing happened. Alert fired. Alert says we're making too much money, something is wrong. And so these alerts are really useful, by the way, because there are bugs. We have had cases where people will log revenue twice or under certain conditions, log revenue incorrectly. So the alerts are normally very useful. But in this case, there was no bug. This simple idea increased Bing's revenue by 12%. Okay, these things never happen. Rarely happen. At the time, this was several years ago, this was $120 million. Now it's worth over $300 million to do such a change. And what was interesting is it did not hurt guardrail metrics. So many of the times when you see an idea that improves revenue, it will hurt the user experience. Right? Typical example is you add more ads. Right? If you add more ads, you're going to make more money, but you're going to hurt the user experience. What was unique about this one is that the guardrail metrics barely moved. This was generally a good thing for revenue and did not hurt the user experience. And so what I want you to remember out of this is we're just terrible at assessing the values of ideas. Right? Here is one of the best ideas in Bing's history, probably the most important revenue-generating idea in Bing's history. There's very few examples that generate over $100 million like this one did. But we delayed it. We didn't know how to assess, how to assign value to it. And this is one of the key themes that I want to share with you, and we'll go through more and more examples of this, that we're just not good at assessing the values of ideas. So before I go into the details about control experiments, I want to actually look at some things that happen in real life that you're probably all familiar with, but I want to make them a little more crisp about things that you see out there, that we see out there, that people evaluate ideas. So here's a few things. First of all, realize that everybody builds features because they believe they're good, right? We rarely build a feature because we think it's going to hurt the user experience, right? We're all sort of positive about this. But the reality is that, that many features fail to improve the metrics that they were designed to improve. And here's sort of an observation of our statistics across a lot of groups at Microsoft. About a third of ideas are positive and statistically significant. You made a good difference. This is what you're aiming for. About a third of ideas are flat, meaning didn't do anything good, didn't do anything bad. Normally we don't like to ship these because they add code, they add complexity, they may have more bugs. And then the third, and this is the surprising part, are negative and statistically significant, meaning they actually hurt the user experience, right? Here we go, we think there's a feature that's going to be good, we expose it to a real A/B test in the real world, and it fails. And then, you know, these slides are available online. There's a lot of references that I can give you. I'm not going to go through the details, but I just want you to know that this is not something that we only observed at Microsoft or at Amazon where I used to work. This happens a lot, and it's been documented over and over again, especially in the software business. We're really bad at assessing the values of ideas. So here's something that we see a lot, and I want to just make sure you're aware of it. Somebody comes along and tells you, hey, I'm looking at churn rate for my users, and I make this interesting observation. If people don't use my feature, they churn at a rate of 25%, right? And we define churn as you stop using the product in the next 30 days. But if people use my feature, only 10% of them churn. Right? And I've seen this statement over and over again. And the key thing to realize is that there is no conclusion that you can make about whether the feature reduces churn or not. Okay? These two statements are correlational, and they said nothing about the cause. And here's an example of what you should say when people say this. Proven fact, users that see error messages in Office 365 churn less. Okay, so that doesn't mean I should start displaying more error messages. Right? All it means is that there is some other factor, in this case, the fact that they're heavier users, that causes two things. One is that they use your feature, in this case, all these features that people claim help them, or they see more errors. And it also means that they have higher retention rate or lower churn rate. Right? Classical example, I'll see this, you know, we've seen this over and over again. Be careful of these things. And if you're interested, there's a link here that I gave to a PowerPoint with some of the best examples we were able to find of observational studies, meaning uncontrolled studies, where people have concluded a causal relationship that was then later on proven to be wrong. Normally wrong through a controlled experiment, which is a higher level of standard, we trust it more. Many of these are in the medical domain. Smart people, doctors, made these observations. They were wrong, and in many cases they caused more deaths, more harm than if you had not used the drug or the recipe or whatever they suggested to use. So lots of really interesting examples, and also the reason why we got fooled by these. Just to conclude with a sort of a fun one, a true observation, if you look at your palm size, it correlates with your life expectancy. So look around at your neighbors. If you have a larger palm, you will live less on average. You're going to live longer than I do, right? Because you have a smaller palm. And of course, the problem is don't try to bandage your hands. There is a common cause. Who knows?
Gender.
Gender, exactly. So women have smaller problems and live 6 years longer on average. So correlations happen a lot. Here's the second thing that people do. This is more solid than the first, which is to look at a time series. Okay, so here's an example of Kindle sales. You have your site A, and they sell, and they sell, and they sell, and then you switch to site B, which you think is better, and boom, there's a nice spike in sales. Can you conclude that your new site in blue is now much better? And the answer is no, and this is all the external factors that can happen. In this case, Oprah saying Kindle is my favorite new thing. Right? So if you are able to run a controlled experiment, you might observe something like this that shows you that B was always inferior to A. Right? The blue is always inferior. There was an external event that caused a massive jump. Both of them are impacted. But which site would you want to use? Obviously, you want to use the green site, which is always better. Okay, so now I showed you a couple of things not to do. By the way, this time series approach is useful if you're able to turn the feature on and off. So quasi-experimental design has cases where you turn it on, then you turn it off, and then you turn it on, and turn it off. And if every time this thing happens, then the chances of an external event is very, very low, but still a lot less reliable than a controlled experiment, which is sort of at the highest standard of scientific causal discovery. So what do you do in an A/B test? Simple. I think most of you are probably familiar with it, so I'll go through this quickly. We have users. We split them into two groups. The control, typically the existing system, right? And we use what's called the champion-challenger model. This is what we think of as the champion. It's the best we know how to do. That's what's live. And then we're trying to challenge it with a new treatment, something that we think is going to be better, right? And so we instrument everything that we can about the system, both on the server side and on the client side, whether it's user clicks, whether it's hovers if we can instrument those, we do that a lot now, performance results on the server, on the client, everything that we can should be instrumented, which data center it was served out of, which browser the users used, everything you can should be instrumented, so that at the end we can do this analysis, right? And what the analysis basically is just trying to figure out if the users that fell into treatment, are their metrics different than in control, and are they positive? So A/B test, which I'm going to basically focus on for simplicity, is just this. It's an A and a B. In reality, we recommend that you run ABN, which is more factors, right? We actually encourage people, if you come up with a new design, with a new idea, don't just test a B version, try to do B, C, D. Maybe one of them is going to be better. So many of our experiments have at least 3 or sometimes 4 factors. We can get into the details. We don't usually run multi-variate or multifactorial designs, because in the software business, it's so easy for us to ship software that it's easy to test ideas and not try to create one gigantic experiment. In the industries, there's lots of names to these things. Microsoft calls these flights. Google calls them 1% test, which, by the way, is a terrible name. We don't ever recommend you do 1% test. Yahoo calls them bucket tests. In medical domains, in Facebook, they're called field experiments or randomized clinical trials. They're all basically the same thing. They're all trying to control the differences between A and B by running them concurrently, so that you can conclude if the differences between them are due to chance or are statistically significant, right? This is why you have to do simple statistical tests, and this is why we say that this can prove causality. Right? And this is one of the key things about a controlled experiment. If the metrics at the end are different and pass the statistical test, that they are statistically significantly different, then you can conclude that with high probability, the change that you introduced in the treatment was the cause for the metrics changing. Okay, let me stop here for a few seconds. Any questions about this? Yeah, question.
So one thing we run into a lot is the business unit will basically want to run what we call pre-post, what you call the time series analysis, and we'll say, no, you should run an A/B test because something can change over time and affect your result. But we really, our best argument for that is something could change over time. Could you talk a little bit about?
Yeah, so I'll go through this briefly again. If it's going to be a long topic, then we can take this offline. But the way we have sort of convinced the organization to avoid these pre-posts is by running AA tests. So in an AA test, there is no difference, right? And like you can feed the same control over here, and then your system should tell you 95% of the time that there is no difference. In pre-post, they fail all the time, right? So take a week before, take a week after, look at them, and you'll see that the metrics diverge a lot. And this is our way for us to show that this is not a reliable mechanism for establishing causality. One of the key things about controlled experiments, I'll talk about in a couple of slides, is the sensitivity that you get. So I think you'll learn a little more in a few slides, and again, I'll be happy to give you more later on. Okay, so we talked about causality. There's basically the changes are causing this, and I'll mention there's many advantages to controlled experiments, but I want to mention a couple of them in this intro, which is sensitivity. Very, very important. You can detect very, very small changes. Right? And this is not something that you can do in a sequential trial or anything like that. To give you an idea, at Bing, for example, we will alert, we can detect differences of 1 to 2 milliseconds in the performance of our system. Right? This is not something anybody could detect with their eyes, certainly not anything that you do pre, but we have such sensitivity on key metrics that we're able to detect that. And the other thing that is really, really interesting in a controlled experiment is that you can detect unexpected consequences. You were changing something, and then something else happened. And I'll share with you examples of these through these slides. So let's go with sensitivity. Time to success is a key metric for Bing, right? Search engine, what you want to do is user issues a query. You want to measure how long does it take them to be successful, and we define the simple definition of success is they click to some destination site and they don't come back quickly, right? So we believe that if they click and they stayed at that site for more than 30 seconds, then they were happy, they were satisfied, right? Simple definition. If you ran a sequential test, here's your A, here's your B, would you be able to say that one of them is better than the other? Now this is real graph. Typical variability that you see is like that. There are days where things are high, things are low, could be impacted by weekends, could be impacted by many news, anything that happens could impact this. But could you say anything? And the answer is very, very hard to say what's going on. But this is a control experiment, right? And I can tell you that both of these ran concurrently, and there was a difference of 0.32%, right? And now you have to ask me, well, is that statistically significant? And I can tell you unlikely, there's a p-value, we'll talk about this more in the presentation, was 0.003. Convention says below 0.05, you accept as statistically significant, so this is statistically significant, at least at that level. The other thing that I can tell you, which is even more convincing in this example, is I can just plot the two over time, right? And when you look at this over time, there's no doubt in your mind that every day, the B version, the treatment, was better than A. It didn't just fluctuate, which happens a lot. This was clearly a winning treatment, and we can see that from this graph. So why is sensitivity so important? Well, so first of all, many metrics are hard to improve. There's a statement that I've heard from many people that, well, if you have enough data, everything becomes statistically significant. We have a lot of data. We have 100 million users of using Bing every month. We run normal experiments on millions of users, and we have a hard time detecting statistical significance. Right? So that sort of statement that in infinity is the asymptote, as you get billions of users, everything becomes statistically significant, doesn't happen in practice. Even with our massive scale, it's hard. The second thing that is significance, that sensitivity is important for, is early alerting. Right? If I ship something and it's bad, I want to be able to detect very, very quickly that it's bad and abort. Right? And that sensitivity allows me to say, with high confidence, you have just degraded some metric. Abort the experiment. Right? And the last thing is, if you're not able to detect small degradations, they could accumulate. Right? You run some experiment, you're not noticing a degradation. You run another experiment, and you're not noticing a degradation. But over time, you are degrading some of your key metrics, and you may not realize it. Right? And I want to give you one example, which is, I think, an amazing example that describes this, is the importance of performance. right? We all think, oh, faster is better, of course, but how? How much is that important? So we ran what's called a slowdown experiment. We actually slowed down Bing to be able to measure the performance, the impact of performance. And this is the result. The key insight is if you're an engineer and you're able to improve the server by 4 milliseconds, right? Your eyes blink at about 150 milliseconds. This is a small number. Nobody can see that. Nobody can detect it. You can't do it in a lab or in an experiment. But if you're able to improve the performance by 4 milliseconds, you just paid your fully loaded annual costs. Right? That 4 millisecond is worth $500,000 to us. We assume a profit margin of about 50%. That funds an engineer. Forever. Right? If their improvement in performance stays, then they keep funding themselves forever. So when we have an experiment and somebody's able to improve performance by 20, 30 milliseconds, that's a huge win. Right? Yeah?
But aren't you extrapolating there? Because you're slowing it down, you see the difference there.
Yeah, so it's an obvious assumption. The assumption is that if I slow it down and I observe a metric, if I speed it up, I will see the opposite. Now the reason we're happy with that, and I can give you more of the details, is we have done this experiment at different slowdowns, and we can see that there's a very linear curve between them. So it is very reliable to assume the opposite. We've also known that when we improve performance, we see everything improve, right? So this whole observation, the whole idea of a slowdown came because there was some change that was made, that somebody made, unbelievable. It's like they figured out how to write JavaScript more effectively, and it improved performance by over 120 milliseconds, right? And we observed all these like tremendous improvements, and so we wanted to make sure we were studying this correctly. It wasn't just the change to the JavaScript that was causing it. So then we ran these slowdown experiments, which we have replicated, and there's papers out there that we published, and Google and others, about the importance of this. Very, very good question. Very, very important. So today, because of this result on performance, we basically stop people from shipping if they're degrading performance by more than a couple of milliseconds, right? That slowdown we know is going to accumulate and hurt us long term. So even if we can't detect small changes on that order, we know from this experiment that every millisecond counts. Yes?
So do you do cost inference? I mean, determine something is wrong is important, but know why something important isn't much, why something wrong is much more important.
Ask the question again. Why the feature?
So, we are you do the cost inference. I mean, determine something's wrong is important, but understand why something's wrong is much more important.
Yeah, so all this tells you is everything else being the same, if something is slower by 4 milliseconds, we lose $500,000.
Yes.
Right? Everything else is the same. Now, which in reality, most people will build a feature and say, is this feature good or bad? But they might impact performance. So today we have the ability to say, if you slow down performance, you might be hurting things like this. We don't allow you to ship until you improve. Or we may say the feature, even if it were equal, we have a mapping that shows for every metric what would happen. We can deduce what would happen to the key metrics. I'm not sure I understand your questions. Let's take this offline if we need to. So the second thing that's critical is unexpected consequences. It is very, very common for somebody to touch a piece of the system and not realize that it's impacting something else. What do we do in that case? We give a lot of metrics when we generate our scorecard from an experiment. Okay, let me give you a sense. Typical experiment on Bing, 2,000 metrics are being produced. Most of them are not going to move because you didn't intend to impact them and you didn't impact them. But we will highlight for you those metrics that you impacted. And that may lead you to understand that you're impacting something that you didn't think would impact. And I want to give you an example. Related searches. So when you do a search, there's a block that's called related searches that will show you, you search for Harry Potter and it says, well, some people search for cast or store or characters or movies or games or books, etc. Now, there's a team that tries to improve their related searches block, and one of the examples that typically they do is they bold the terms. You know, if you search for Harry Potter, maybe I should bold Harry Potter, right? And what they will observe is that when you bold something, people click more, which is expected, right? It's not no magic. You make something bigger or bolder, people will click more. But the interesting thing here, when the first experiment started on this, is they didn't realize they were impacting the whole distribution of queries, right? Because they're now prompting people with these queries that are more head, meaning that are more common, we're shifting the distribution of queries to head queries, and that has impact on things like revenue, right? So here's a change that I made to a local block. I'm trying to improve the click-through, but what I did indirectly is I impacted the whole distribution of queries on Bing, and that has profound implications. So that's an example of something very, very important to do. So I mentioned to you there's about 2,000 metrics people pick. There's 6,000 that we define. There's about 2,000 for typical groups that do this, and this allows them to see the unexpected consequences of their experiment. Okay, so now I'm going to have some fun. I'm going to show you 3 examples that ran at Microsoft. Okay, each of them has some key lessons that I want to share with you. They all had enough users for statistical significance, and for each experiment I will give you the OEC, which is the overall evaluation criterion, and this is a key criterion. This is the thing that determines whether the A or the B wins, right? So we're going to pick simple OECs here. In reality, they're a little more complex. And then I just, want to give you the chance to see how many you get right. So I know some of you are tired. It's after lunch, but I'm going to ask you to please stand up. Everybody, thank you very much. And I'm going to ask you an A/B test, and there are basically 3 options. Okay, you either raise your left hand or your right hand, or you don't raise any hand. Okay, if you get something wrong, I'm going to ask you to sit down, and we'll just see at the end of the 3 questions how many of them you get right. And I'll just point out that if everything's completely random, you're going to have 4% of people standing up. Hopefully this room is going to be much smarter than 4% random. So we'll see how well you do. So the first example is the Windows search box. Okay, if you've used Windows, after Windows 8, there is a little search box in the taskbar on the lower left. And that runs on a lot of machines. And here are the 2 variants that I'm going to ask you. One of them says, search the web in Windows. And the other one says, type here the search. Right? And we're going to ask the OEC, which is better, is the one that causes more engagement, meaning more searches, and hence more Bing revenue. So I'll just point out a few things about here. This is more informative because it tells the user we're going to search both the web and your Windows box, so we might find it something in your local file. This is simpler, may not explain it more, so it's a tough call to decide which one is going to be more important. Okay, so raise your left hand if you think the left version wins. Raise your right hand if you think the right version wins, and these are stat sig. And don't raise your hand if you think they're doing about the same, so there is no statistically significant difference between the 2. Here's how I want you to look around. So first of all, a couple observations. Most people know the answer, right? Very few people are not raising any hand. But there's a lot of conflict. Some people are raising their right hand, some people are raising their left hand. This is very, very typical, by the way. So if you did not raise your hand, you were wrong. Please sit down. If you raise your left hand, you were wrong. Please sit down. And if you raise your right hand, you're either good, lucky, or looked at the bottom left of your machine, which shows you the right answer. But this is interesting. So please stand up if you got this right. This shipped just a couple of months ago. What was before it? There's actually 4 variants that we tried. Type here to search, which one? That's the one that I showed you. What can I help you find? Ask me anything, or search the web in Windows. The one that shipped with Windows, which the designers and the smart people picked, was 3rd on this list. Right? So for 2 years, we had something that was suboptimal, and all we had to do was run this experiment, and it was just worth a few $1 million. Right? Not bad for a simple A/B test. You had a question?
Yeah, may I ask what prompted you to try version 1 if you already had something working? Why did you?
Oh, this is several $1 million.
No, I know. Type here to search. Who came up with that?
Oh, so that's what I'm saying. There's program managers, there's designers, they sit down and they meditate and they say, this is the design.
Ronnie, can I say something?
This is, yeah, go ahead, Paul.
It started with 12.
Oh,
So there,
wow.
so there was a wider net and we narrowed down.
Oh, okay.
Yeah.
So did you test this with entire population or you sample the subset of the
So
clients.
this experiment, I believe, Paul may be right, it's like 20% experiment?
Yeah, 20%.
Yeah, so we run the typical experiment with 20% of our users. So
Okay.
we first tried internally at Microsoft to see that, this is not bad. Then we started a small sample to see, of the users to see if there's an alert that we can generate, and then we ramp it up typically to 20%.
Those 20% are the ones getting the auto for different, like 5%
So, I
each
mean,
of them, or
well, basically, 20% get this, 20% get this, 20% get this, 20%
It
get
was
this.
5. I mean, it's
Yeah, that's
20,
right.
20 total. This is actually 5, which is lower than what
Yeah.
we recommend. Like.
Okay,
Okay.
yeah.
So like
So
5%
do you have a
versus.
user lab or something when you try to?
Yeah, so these, as I said, some PMs might do sketches, they might run this through some usability labs, but at the end of the day, you cannot in the usability lab detect these. These differences are too small, they translate into millions of dollars, but they're just not detectable in a lab, right? And the whole point is, yes, if you delay those decisions, and the beauty about this is that they built this feature in a smart way. It's driven by the server. So every few hours, your Windows box says, hey, what should I put in this string here? Right, and that allowed us to run this experiment. So the ability to write your software in a configurable manner is important and is a key lesson that we're learning more and more in organizations like Windows, which used to ship and forget. Okay, second example, SERP truncation. SERP.
Copy is great here because it's cheap to change, ideas are cheap, and impact is usually massive. Copy is hugely underestimated.
Okay, SERP truncation. SERP stands for the search engine results page. This is typically, you type some search like KDD, you get a result. It has the algorithmic results on the left here. It has what's called the task pane on the right, which sometimes explains more. But I'm going to show you something that sort of is an interesting observation. And we're going to try to optimize something obvious, which is click-through rate. So, I displayed the SERP. And I want you to click through and to simplify things. Again, in reality, life is more complicated. There are issues with people coming in and going back, clicking twice. I'm just going to say, forget all that. Just look at the first SERP per query and see what the click-through rate on that, right? And so what did we observe? We observed that, as you expect, most people click on one, then less. And we said, what happens if we truncated the page, right? So instead of showing 10 results, which is the classical 10 blue links everybody knows about, we're going to show only 8 results, and we're just going to chop off the bottom, right? So nothing smart, again, trivial to implement. The server computes everything it wants to do instead of sending the 10 to the clients, we just send 8 to the clients. Everything else we keep the same. So if there were ads on the page, if there are related searches, if there the task pane, everything else remain exactly the same. I will point out that version B is slightly faster because it is sending fewer results to the client, which means there's less HTML on the wire. Because this was implemented cheaply, the server side computed exactly the same. So the server actually generated 10, we just shipped 8 of them to the client. So it's a small performance improvement. So now raise your left hand if you think A wins, meaning display 10 results. Raise your right hand if you think B wins, meaning displaying 8 results. Don't raise your hand if you think they're doing about the same. Okay, so notice again, most people are highly opinionated. You're wrong. If you raise any hand, please sit down. So this is something that we documented, and it's a very surprising result. It's one, we looked at thousands of experiments that we ran and tried to find some patterns in a paper called Rules of Thumb. And one of them is, it is very, very hard to change the click-through rate on the page. Right? Or because there's multiple clicks, we called it abandonment rate. But we can chop off 1, 2, 3. At some point, the page becomes too white, and people start reporting bugs. But if you look at this page, if it has what we call the D card, which is a fat result with sort of intermediate results, we actually truncated these to 4 results. So we would cut here because we knew your screen, you wouldn't notice that there's nothing below, and nothing happened to click-through rate. Right? All we did was move people up from these things. So they used to click on the bottom, now people are clicking in here, and this is very, very common. You add something to the page, you might think you're getting clicks on it, it's cannibalizing the rest of the page. Right? There's very few examples where we know that we've changed the click-through rate. Yes?
So even though there weren't any changes, did you end up shipping with your results?
Yes.
Or did you ship less?
Yes, in fact, we utilize this to do something smart, which has to do with the second page. Bing, if you go to Bing, you'll get 8 today. But if you click and come back, you'll get 14. Okay, so the observation was, well, if you come back, you're probably going to have to go lower on the page. So we want to show you more results, right? So it did ship, and there's an article that that posted on some Bing blog to say that we've made this change. Nobody noticed these things, by the way. It's very, very hard to see this. Okay, so there's obvious exceptions, but basically this was a pretty interesting result. And then we've tested a lot of things. So for example, we would remove related searches from the page, and everybody would click someplace else, and it would have no effect. Or we would put the related searches below the ads, or after the ads. All these things are basically moving clicks around, but the end result, the click-through rate, the thing that we care about, stays the same. Okay, let me go to the last example. Bing ads with site links. So one question is, should we display site links on ads? Here's a simple example. You do a query. It has no site links. You don't know where you'll end up when you click here, right? You'll end up on e-insurance, auto insurance, but you don't know the details. On the right, and this was the proposal, the user would be more informed. We would tell them, get a quote, find discount, how about you want to know about Allstate, and compare rates, right? So this has more information. The OEC, by the way, is going to be revenue, which is, we like revenue as a metric. But the problem with revenue alone is that if all I did was say revenue, then I can tell you this would win. This would win because it's bigger. If you make something bigger, it gets more clicks, it will get more money. But the problem with adding more ads or bigger ads is that we know ads hurt the user experience. We've proven over and over again that when we add ads, the user metrics degrade. So we've put a constraint on ourselves, which is the ads team can only use a certain number of vertical pixels on average. So you look at all the queries, they're allowed to put a lot of ads on some queries, 0 ads on some queries. We compute the average pixels that they have used, vertical pixels, right? So the fact that they have this constraint means that they can have 4 of A against 3 of B, okay, which is what makes this very interesting. So if they want to put a bigger ad that's got these site links, they will be able to, they're going to use more vertical pixels, and so they will have to somehow use fewer of those versus A, and the ratio, because it's 3 lines versus 4 lines, is as you expect, 3 to 4. And there's another thing, which is B is a little slower. Again, it's got more HTML, takes a little longer to compute, but it's only 5 milliseconds. Okay? So raise your left hand if you think left version wins, meaning it generates more revenue for the same constraint. Raise your right hand if you think the right version wins, and don't raise your hand if you think they're doing about the same. Let's see who doesn't vote here. There's a couple, 1, 2, 3, 4 that don't vote. Please sit down if you did not raise your hand. If you raise your left hand, you were wrong. Please sit down. If you did not raise your hand, you were wrong. And site links generated tens of millions of dollars more for Bing. Okay, so what do we get? 1, 2, 3, 4, 5, 6. Thank you, folks. Those of you that got this right, you can come to the booth and we'll give you an EXP shirt. And you can submit your resume over here. No. A little better than luck. So if you think about the room here, 4% would probably be about 4 people. We got 6 people. So it's kind of hard to say this is a statistically significant difference. We're much smarter than random luck. Okay, so the point is stop debating, get the data. I want to talk about scale. This is the tutorial about A/B testing at scale. I want to give you a sense for the scale of experiments that we run. We run now over 1,000 experiment treatments per month just on Bing. We're now ramping up a lot of other groups at Microsoft. Everybody's starting now to run experiments, whether it's Office or Xbox. Multiple organizations at Microsoft are now realizing that this is the better way to develop software, and that's what we're doing. So what are the things that happen? So first of all, the typical treatment is exposed to millions of users, sometimes tens of millions of dollars. So when we have a surprising result, we're not sure about it, we will actually rerun it, which is very, very important. The hallmark is sort of replication, but we will also make it larger so that we have smaller p-values if the same effect holds. This is an interesting observation. There is no such thing as Bing anymore. Right? If you think about it, a typical user is exposed to at least 15 concurrent experiments. Okay, so that means, and these experiments, and this is a little bit of math, I don't want to go into them, but we have the user base, and we split the user base into chunks of 20% that are getting a treatment, and so 5 of them are basically filling the whole user base, and so it turns out that you're in 5 to the 15, or 1 of 30 billion possible variants of Bing when you visit us. Okay, and that means that debugging takes a new meaning. When there's an error, when somebody reports something, we have to always associate and say, which experiments were they in, which treatments they were in. Let's try to replicate that. Yep.
You mentioned that you wouldn't recommend multivariate, but it seems like if you're in 15 concurrent experiments, you'd be on multivariate.
Right, so a user is in a lot of experiments. These are not the classical multivariable designs where you try to sort of limit exposure and decide, how to do the factorial designs. They're all concurrent. You can think of it as a full factorial. But they also start and end at different times. We rarely do multivariable analyses, right? And again, I can give you more information. The main reason for that is that we are seeing relatively few interactions, and again, there's reasons behind this. So the multivariable has less value. And the other thing is when you do a big multivariable design, you have 6 factors, one of them goes wrong, you have to shut down the experiment. We don't like that. We'd rather have things launching all the time. So every day some 20, 30 experiments start, right? And sort of the agility is worth a lot more than the risk that we're taking that there's an interaction. And we do tests for interaction every night, so we do know if there's some interaction, and then we either convert this into a multivariable or we run them sequentially or do something like that. The other thing is if you run a multivariable that's small, you can just lay it out and say this is 4 treatments or 8 treatments or whatever.
Are you able to ensure that there's no bias generated if different users are in different experiments at the same time?
No, so again, I can take you through the math here, but because you're running a controlled experiment, your control and your treatment are exposed to the same proportions of the other experiments. So the only problem that happens is if there is a strong interaction. And the fact that you're running impacts another experiment in a way that's not symmetric for control and treatment. We test for that every night. Right? So every night we look at all pairs of experiments and test for interactions. And it's rare. I'll just tell you, it's a fact. It happens only a few times, maybe once a week or once every few weeks that we get such an alert. And I think Pablo's going to talk about this more.
Even if you try to control for it, your competition is also running experiments.
Okay, in terms of growth, this is sort of the growth that happened. You can see the sort of exponential growth where we first were limited by the system, and then over time we open up and allow concurrent experiments and everything. And then we stabilize at some point. At this point, there's basically, the limit is the ability for the engineering team to generate features and code. Right? So at some point, you grow, and then the way to grow this is basically to have people write more features. We are no longer a factor in the limit. This is a point that I like to make, which is very important, which is we showed you the cool examples, right? This thing that was a small change that created a massive 12% impact to revenue. These are rare. Very, very rare. Most progress is made inch by inch by people running experiments and making very, very small improvements. And so this is a graph of revenue over time. This is what's called RPM, or revenue per 1,000 queries. And I'm not going to show you the y-axis because this is confidential, but I will point you to a sort that says we grew revenue 55% during this period. And so you get an idea for the beginning and end what the improvement was. But this is not coming from 1 or 2 small experiments. This is coming from a huge number of experiments that ran. And every month, after running a lot of experiments, the ads team will lump them all together and then be able to assess the lift to revenue that happens from that combination of a month of experiments. Right? And you see these numbers are small. They're, they're 1%, 0.6, 0.2, 2.1. Sometimes they do a cleanup, they lose money. And you can see how variable the data is, right? Come Christmas time, end of the year, holidays, there's a lot more money that we make because there's a lot more intention to buy. So we'll place more ads, but you also see that, here they generate a massive lift, but it looks like revenue is going down. And these are basically due to seasonality effects. So most of life looks like this. Lots of experiments, small wins on the order of less than 1%. They just add up over time. Okay, so a few pitfalls. The first one is know what you're optimizing for. This idea called OEC. Right? Very, very critical. We have lots of times where people will tell us, we think we are optimizing for X, and it turns out this is not the case. And I love this example. Microsoft support team comes to me and says, we want to start experimenting. And I said, think about it, come back, tell us what you're optimizing for. Lots of smart people in the room. They said, Ronnie, we read your papers. We're optimizing for time on site. And I say, wait, is more time better or more time worse because you're a support site? Now half the people split. Right? So that means they don't know what they're optimizing for. And sometimes, as in the case of a support site, it's hard because you're optimizing for user success. It's not always easy to know if you have achieved that. A couple of more examples. Again, there's a lot of words on this slide, so I don't want to go into the details. But we are optimizing at Bing for query share. Right? We want to get a larger percent of queries, say in the US, where we're now about 22%. Right? 22% of queries in the US come to Bing, 4% go to Google. We're trying to move that number, and in fact, we've moved it. When we started Bing, it was 8%. We're now up to 22%, so we made significant progress. But this is our long-term aspiration to improve query share. Is it a good metric for an experiment? And the answer is no, it's a terrible metric. Right? We'll talk about this more later on in the other presentations, but it turns out that you don't want to improve queries. You want to improve the number of sessions that a user comes in, and every session should have few queries. So I think Pavel or somebody else will talk about this more, but clearly this is a bad metric, and so that's why something like sessions per user is a much, much better metric to use. Let me skip this one given the time. This is a real example. This is another one, bad example. Misinterpreting p-values, again, we'll talk about this more so you'll get more of a feel for this. But lots of people sort of misinterpret what p-value means. These are some statements. They're all incorrect. I'm going to leave more to Lucas to take you through some of these. But it doesn't, if you have a p-value, it doesn't mean that you have a, the p-value is 0.05, it doesn't mean that you have a 5% chance of making a false positive mistake. In one line, basically the p-value gives us this conditional probability of X being more extreme given the null hypothesis. We really want the opposite, and this is where you need to apply Bayes' rule or something else to fix that. Failing to validate the experimentation system, very, very important. We've seen people that produce p-values that look like 7 digits of precision. They get the first one wrong. Getting numbers is easy, getting numbers you can trust is hard. We spend a lot of time making sure that our system is valid. Also, the books don't do a good job of helping these. These are fun books, good examples, nice to read. They all get the math wrong. Right? They're telling you to do things, and they all get the math wrong here. What do? We run a lot of AA tests. Remember, A and B tests, they're different, and AA tests are the same. If you run a lot of AA tests, you should only get statistically significant difference about 5% of the time. I'll give you one example of a wonderful test that we do called a sample ratio mismatch. If you're designing a test to go 10% control, 10% treatment, you should get approximately the same number of users in control and in treatment. Here's a real example. I got 821,000 users, 588 in one. I got 815, 482 in the other. It's 50.2%. Should be 50. Is that valid or that's not valid? Well, do the test. But if you do the test, the p-value is 1.8 e minus 6. That means such a split of 50.2 with these large numbers should happen 1 in 500,000 times. You have a bug in your system. This test fires for us about once a week. Meaning some design, some place, somebody doesn't do something right. And this helps us understand that the experiment is invalid. And we actually hide the results in that point and say, hey, you have a sample ratio mismatch. Find out what happens. Here's another typical example of an AA test. You want to run a lot of them. You want to look at the p-values. It turns out that if the If you're running a true AA test, the p-value should be uniform. This does not look very uniform. So you know there's something wrong with your calculation of the standard deviation or variance. And this is after we apply correction. And this is because the normal formula that you use makes assumptions that do not hold, such as when you're running experiments on a unit which is lower than the user, like on pages or things like that. Here's another example that I want to share. We did this thing, MSN page. It has an info pane, a large area in the middle, which rotates images. The control had 12 slides. The treatment had 16 slides. Which one's better? Control was much better than the treatment, right? And this was kind of a surprise because we know that competition raised the number of slides and they shipped it. What was the problem? This result came with a sample ratio mismatch, again 49.8 instead of 50. So we knew there was a problem. Anybody think why you'd get a sample ratio mismatch? You yelled control. Why would you get a sample ratio mismatch? Okay. It's a pretty tough one, but the engagement was so good on treatment that the heaviest users were being classified as bots and removed. Okay, so very, very serious problem, hard to detect. We were able to see this because there was a sample ratio mismatch. Actually, treatment was better in this case, as we expected. Failing to validate data quality, outliers cause a big skew. Here's an example from sort of Amazon. We were noticing that a single user could skew the whole A/B test, right? And it turns out that those single users were libraries, right? So a library goes and buys a whole shitload of books. That can be big enough to skew. So you may want to use truncated metrics or do some sort of validation. But that's an important thing to realize that this can happen to you. So we sometimes will truncate to the 99th percentile of a distribution or things like that. We have bots causing problems. This is just an amazing statistics. Over half our traffic at Bing, half the traffic at Bing comes from bots. Okay, lots of people are trying to optimize for things. And I even see this car in Seattle once in a while. This license plate is bot. Must be making a lot of money. Okay, best data scientists are skeptics. The most common bias that we have is to accept good results and investigate bad results. I want to encourage you to think about Twyman's law. Any figure that looks interesting or different is usually wrong. Everybody's laughing, but we call Twyman's law a lot. And we said this is unlikely to be true. And it saves us a lot. So be careful about that. There's actually a book that actually called this the most important single law in all of data analysis. Okay, I want to conclude in the next 5 minutes with a little bit about the culture. This is, Microsoft's a large company. It grew up on CDs in the past, and it's hard to change the culture. So we've gone through a lot of teams and convinced them, but I love this statement. It's difficult to get a man to understand something when his salary depends upon him not understanding it. So people avoid controlled experiments because some of them think I'm the decision maker. Now I suddenly have to revert to this technology, right? Program managers typically define the next set of features. It used to be that Office used to release every 3 years. There was a long planning process. Program managers decide what would be the best features, and then they would chip out. Now they have to come up with ideas, and they're going to be wrong half the time, right? So problem. It's hurt your professional standing. I've heard, we know what to do. It's in our DNA, right? It's in our DNA until we start to test it, then it suddenly doesn't, the DNA is not that good. Why do we do just the right thing? This is an amazing statement, right? We don't know, right? We make so many mistakes. So groups that have experienced this understand that these are very, very hard things to do. So we created this model, which I'll share with you. It's a fun model. The first one is basically hubris, right? We know what to do, we're sure of it. I'll share with you a true story that depicts this really, really well. 1849, John Snow was the first person to claim that cholera was caused by polluted water. Everybody else at the time thought it was bad air. So this landlord has tenants, they're complaining that the water stinks and people are dying of cholera, but he's sure there's nothing to do with the water, right? So in order to prove this, he comes to the tenants and says, hey, look you guys, there's nothing wrong with it. Let me drink it for you. and then he dies 3 days later. So that's hubris, right? It's like, if you go here to the museum, the Maritime Museum about the Titanic, there's a nice quote on the wall saying, I can't think this ship is unsinkable, right? I can't imagine anything wrong that could happen to this ship. So if you're sure about ideas, just try to test them once in a while. Okay, the next stage is measurement and control. Amazing story of Semmelweis. He's a doctor. He works at Vienna General Hospital. It's an important teaching and research hospital in the 1830s. And there's a disease, most of you probably never heard about it, called childbed fever. It killed more than 1 million women that were giving birth. And so what he does in the hospital is he first starts to measure the mortality rate. And he notices that in his ward, 15% of women die. But just think about this, like 1 in 6 or 7 die in his ward. And the reason this is so shocking is there's another ward where it's 2%. And it's attended by midwives. They don't have doctors in that ward. And so he's kind of surprised, and he starts to try to control the differences. I mean, is it possible that he's getting the harder cases? No, it's random. Is it possible that they give birth to different positions? Is it ventilation? Is it miasmas in the air? Is it the food? He goes all the way to laundry. Nothing is able to explain this massive difference. Then he goes on sabbatical for 4 months, and the students come back and tell him, hey, you were gone. Look at that. Death rate is significantly down. So he concludes the painful point, which is it's related to him. Okay, how can it be related to him? Well, it turns out it's a teaching hospital, and his insight is that the doctors are doing these autopsies every morning as they teach the students on the cadavers of women that died yesterday. Right? And they do these autopsies, and then they go and help the women give birth, and they don't wash their hands in between. And so today this looks crazy, but at the time, he comes up with this conjecture that there's particles that we can't see, that are called germs, that are being transmitted to the healthy patients on their hands of the doctors. So he experiments with cleansing agents. He comes up with chlorine and lime, and the death rate goes from 18% to 1%. Right? Beautiful success story, right? Wrong. So this is stage 3. Nobody believes you. Right? Happens often. You come up with the results, it's surprising, it's against intuition, people don't believe you. So what happens? Nobody believes him, he gets dropped from the post at the hospital, he goes to Hungary, by the way, does the same thing, reduces it to less than 1%. They publish a paper, and the editor writes that this is hogwash. Can't be true, where are these particles, why can't we see them, this is not scientific. He has a nervous breakdown and gets beaten at a mental hospital and dies. And today we call this the Semmelweis reflex, right? So if you look at Wikipedia, it's a reflex-like rejection of new knowledge because it contradicts the norms and beliefs that we have today. You will see this organizations when you come up with a surprising result. Now, is this only in the 1800s? No, if you look at a study from 2005, inadequate hand washing is the prime contributor to 2 million healthcare-associated infections and 90,000 deaths annually in the United States alone. Even though this was proven a long time ago, we still don't get to wash our hands sufficiently. Okay, and then at the end, what is the final stage? Is this fundamental understanding. So in 1879, Louis Pasteur showed that the presence of strep in the blood of women is really associated with childbed fever. Took a long time, 143 years later, there's now a 50-euro coin commemorating Semmelweis. So think about these sort of evolution of the culture. We see that a lot. Organizations initially are sure they know what they want, and they start to measure and they realize they're not that good. There's sometimes this reflex to reject stuff, but at the end, we believe we make the forward progress and get these. I want to conclude with one slide on ethics. There have been several controversial examples of A/B testing. Facebook ran this emotional contagion experiment where they were trying to show people either happy or sad results to see if they can make an impact. They did make an impact. Amazon ran a pricing experiment. OkCupid had a math score when they decided to show people that they're matched 90% when it was really 30%. These are controversial. I probably wouldn't do some of these. But I want to just refer you to resources. There's a famous Belmont report based on some really early medical research where people were denied treatment in order to run an experiment for 40 years. So now there's some standards about what you can do in the government. This does not impact companies in the wild. But this evolved in '91 to what's called a common rule, and I think the key concept is what's called minimal risk, right? Which is you're exposing people to some treatment, and there is minimal risk if the magnitude of the harm is going to be what you are normally subjected to in daily life. By far, most of our experiments fall into minimal risk, right? We do something, we change something, it's minimal risk. But if you're running something that is more than that, you should consider some review, and there's a concept called the Institutional Review Board for you to use. Okay, so last slide, the fun one on the HIPPO. So there's a bunch of them. If you haven't grabbed one from the back, they're available. HIPPO stands for the highest paid person's opinion. We created this acronym and the little HIPPO toy to get our organization to change. This is an amazing fact. Hippos kill more humans than any other non-human mammal, mostly in Africa. They're very big animals. People step on them in the dark and they die. But listen to your customers. Right? Don't let the hippos kill your good ideas. And then I mentioned this, and there's a bunch of booklets in the back. So, summary: less the data, the stronger the opinion. Make sure you get the data. Think about what you're optimizing for. Listen to your customers and get the data. Prepare to be humble. Data trumps intuition, and it's a cultural challenge. Look at your statistics carefully. I mean, this is well known from the 1920s, how to run a t-test. But there's some complications that happen in real life and efficiency considerations. So we've documented a lot of these. Again, there's booklets in the back if you want to read some of the papers. And then run experiment often, because if you have a certain failure rate on your experiments, if you run the crank faster, you'll be able to do better.